Okay, example 6 says graph the logarithmic function, state domain, range, and vertical asymptote. So again, we want to make sure we have our domain, our range, and our vertical asymptote. So remember, the range is always negative infinity to positive infinity. Our vertical asymptote can be found by identifying what our h value is. So our h in our case is 5, but remember it's the opposite. So it's going to be x equals negative 5. So when I'm looking at my domain for this graph, I have to just be mindful that I'm going to have to start at negative infinity negative 5 and carry all the way out to positive infinity because that's where my vertical asymptote is, as well as I don't have any negatives in front of my logarithm. So at negative 5, 1, 2, here's asymptote. So with this, I can go ahead and plug it into my calculator, which I want to hit clear or y equals and clear all of this information. To make sure I have the right input, I go to math, scroll to log base, press enter, and I put in my base is 4. Inside the parentheses will be x plus 5. Outside the parentheses will be plus 3, and I will graph it. From here, I want to go ahead and look at the table, so second table, and I'm going to choose points. So I may choose -1, -4 maybe, just thinking about like what's a whole number. And I may choose to stop at -4, so I'll choose -4, -1. No, I'll do -4, -3, and -1. So x equals y, -4, -3, and -1. So at -4, it was 3. So I have 3, 3.5, I believe. Yep, 3.5 and so common logarithms. Common logarithms are logarithms with base 10. So very important that you understand common logs have base 10. And is denoted by the notation log of x. So if you don't see a base, you have to assume that it is the value of 10. The natural logarithms, these are with base e, which are natural logs, and it's denoted as ln of x. So when you see ln x, that simply means it's the log with the base of e of x. So notice this notation, ln of x equals y, can be rewritten in the exponential form as e to the y power equals x. So just taking on the rotation that you may need in order to make this happen. Remember, e changes to ln. So that's just a key thing you may want to note down. So example 7 says evaluate the expression. Remember, when we're evaluating something, we set it equal to the question mark. So in this case, we're going to change things into exponential so we can figure out what that question mark may be. So since we have no base here, we assume that it is 10. So we're asking ourselves 10 to what power gives us the 0.001. So we can think of this 0.001 as saying 1 over 1,000. It's the same as writing 1 over 1,000. So 10 to what power gives me 1 over 1,000? Well, that question mark will equal -3. Part B, same concept, set it equal to the question mark. So I have a base of 10. So I'm asking myself 10 to what power gives me 10 to the 8th power? Because I have a value here and I have an exponential value of 8. So that means based on those rules that we started with, rules 1 through 4, that tells me that the question mark is going to equal 8. So revisit those rules 1 through 4 in the first video. Part C says ln of 1 over e equals what? So remember, we have ln of 1 over e. It's asking us e to what power equals 1 over e. So anything that will cause us to have a fraction would make the question mark equal -1. So if I put that to the -1 power, that gives me 1 over e. And then part D, this is very similar to rules 1 through 4, and I'll even go back to those. So when I look at rules 1 through 4, the question D looks very similar to question number 4, except that log A of x is replaced with the ln of 3.2. So if I look at that rule, very similar to the ln of 32, or just ln, anything e to the ln can be rewritten as ln question mark will give you ln of 3.2. That's ultimately what it's meaning when looking at number 4 from those statements. So that means that 3.2 is going to equal our question mark. So also just understanding that, like I said, E and ln are exactly the same. So when you have these setups here, they ultimately cancel out and become 1, and you're just left with whatever that x value, quote unquote, is going to be your answer. For the domain and range of these logarithms, I'm going to allow you all to put them in your calculator and go ahead and graph the functions and find out exactly what your domains is. So remember, you need to make sure you use the base value, which is going to be that log base. So you can put in the base of 4 and the base of 5. When you put it in, graph it, see if you get the value of domain being from -6 to infinity. For B, I want you to go ahead and check that as well. You should have 2 different domains. Your domain should go from -infinity to -3, union 3 to infinity. So use your graphing calculator to check these and verify that you get these domains from your graph. All right, so let's look at some application problems. How long will it take a bacteria that grows at an hour rate of 25% to double? So in this case, we are going to use P, or A equals P times E to the RT, the natural log for continuous compound interest. So remember, continuous, you can tell you're using continuous because it says how long will it take a bacteria that grows at an hourly rate, which hourly means it's continuous. So that's why we use the formula A equals P E to the RT. So I like to go ahead and list out exactly what I may know and what I might need to find out. So one thing I can look for is the rate. The rate is 0.25. I know that I don't quite know my time because it just says that it grows at an hourly rate. So it's not necessarily knowing exactly what my time may be. But I do know some information here that talks about it doubling. So at 25% to double is ultimately what I'm looking at here. So my A value, being that it doubles that 25%, is 2 times x. So it doubles whatever the x value may be. And then I know that my principal is going to have to be the x value. So how long will it take a bacteria that grows at an hourly rate of 25% to double? Well, if my principal is x, that means that my answer would have to be double the amount of x because it's asking me at an hourly rate, 25% of that has to double. So I kind of have this set up here, which means I don't know what my t value is. So setting this up, A is now 2x equals my principal, which is x, e to the rate, which is 0.25 times t. So I can divide both sides by x first to kind of get e by itself. So I get 2 equals e to the 0.25 times t. And when solving this, I have to take the logarithm or the natural log of both sides so I can get rid of this e value. So I'm going to go ahead and take ln of 2 equals, when I take the ln on the right side, I move the value of 0.25t to the front, and then I take the ln of e. So moving that 0.25 to the front, that you can take the ln of both sides. So ln of 2 equals, well, I know ln of e is automatically 1 based on rules. So I'm just left with 0.25t. My goal is to solve for t, so divide by 0.25 on both sides. T is going to equal, plug it in your calculator. So clear this, second quit. When you plug it in your calculator, you're going to do alpha y equals, so you can get a fraction. Your ln button is right below the log, so ln of 2, close your parentheses, go scroll down, and you're going to hit 0.25, and that'll give you roughly about 2.8 hours. So about 2.8 hours is how long it will take. Let's look at a certain element has a half-life of 5,700 years. At what rate does this element decay? So key thing here is our half-life and the word decay. So we know we're going to use this formula, A equals P times E to the RT. Whereas I'm dealing with the element that is in half-life over a certain amount of years, things that I'm missing that I know I don't see is my rate. So I know my time is 5,700 years. I can identify what my A and my P value is. So I'm talking about half-life. So a certain element has a half-life. So the amount that I'm looking for is X. So I don't know what that principle is. But I do know that a certain element has a half-life of 5,700 years. So I know that my A is a half of whatever my principle is. And I don't know the rate. So that means I have a half X equals an X times E to the R times 5,700. So I'm going to go ahead and divide both sides by X, very similar to the last example. So I have a half equals E to the 5,700 times R. So again, my goal is to get rid of E. So I'm going to take the natural log, or ln, of both sides. But remember, when I take ln of the right side, I have to bring down that exponent. So it'll be 5,700 R ln E. So ln E, so I have ln of a half equals 5,700 R. Divide both sides by 5,700. R is going to equal, put it in our calculator. So I'll do alpha y equals, and well, first I need to go ahead and put the ln at the top. So I'll have ln. Go ahead and put alpha y equals again so it forms the fraction for our half. So we have 1 over 2. Scroll over to the right so it gets your cursor from underneath the bottom. Scroll down to the bottom after you close your parentheses and you have 5,700. Press enter, and we get about negative 1.26, and we have that negative 4 out here on the outside, which tells me I need to move my decimal place to the left 4 units. So I get 0.00012, so about a rate of 0.012% decay. That's all I have for you all. Make sure you take care of both homeworks for 4.2 and 4.3. See you all tomorrow.